So let us take some applications of this hyperconjugation or pi sigma conjugation or no bond resonance and so on, whatever it is. Hyperconjugation applications. There are number of applications are there, because sometimes in a given chapter resonance may not be there. For example, in alkenes chapter resonance will not come, because alkenes have no double bond. So pi bond is a must for the resonance. So in the alkenes resonance concept and mesomeric effect will not come at all. But hyperconjugation is there in almost all the chapters without any exception, because even if the compound starting material and end compounds both are saturated without any pi bond, but they passes through the carbocation. So the carbocations show hyperconjugation. So double bond, if it is there, hyperconjugation will come. Triple bond, alkenes and alkynes, benzene, carbonyl compounds, aldehydes, acids, ketones, acid derivatives, all the compounds, even though their compounds are saturated, their intermediates or carbocations or free radicals will be there. So in such cases, almost in all the chapters hyperconjugation will be there. So therefore the hyperconjugation is slightly difficult to understand also, and it is spread over in all the entire organic chemistry chapters. So let us see some of the, at least some applications we will take. The simplest application is stability of the alkenes. If the two alkenes having the same molecular formula like C4H8 with this formula, that means number of carbons, hydrogens and all that is almost same under given conditions, that is a CH3, a CH2, CH double bond. This is called 1-butene, right? The other one is 2-butene, CH3, CH double bond, CH3. So if these two compounds, when you burn it and either add double bond, saturate it, or burn it with the excess of oxygen, you will get 4 molecules of carbon dioxide, 8 hydrogens, so 4 H2O molecules are formed, plus some energy is liberated. This energy per mole, if you calculate, that is called heat of combustion, heat of, when you burning into the total oxidized products, so energy is called heat of combustion. So heat of combustion of 1-butene and heat of combustion of 2-butene, if you compare, and the products will be same, but the energy E1 and E2 is not same. E1, E2 are not same, isn't it? Same energy is not found. Though the products are same, but the compound's stability is different now. How can you justify? Means here there are 2 hyperconjugations are there, here 6 hyperconjugations. So as just like in the resonance phenomena, more the resonance structures, more stability, more hyperconjugable protons, more will be the stable. So more stable means if you write a potential diagram like this, okay, this is the 1-butene will have a slightly potential energy. I am showing on the y-axis potential energy increase. This side reaction progress I am showing, okay, on the x-axis reaction progress, the potential energy. So 1-butene will be higher potential energy when compared with the 2-butene. The potential energy of 1-butene, 2-butene are different. 2-butene is less potential energy, more stable, and both are converted to a compound called carbon dioxide, right? So both are giving carbon dioxides only, isn't it? So therefore, which gives the more energy? 1-butene gives the more energy. This is 1-butene energy. This is 2-butene energy. So the 1-butene gives a E1 energy. 2-butene gives a E2 energy, which will be always lesser energy, lower energy, because the molecule already stable. Stable molecules will have a less potential energy. Therefore, it is demonstrated practically. Take 1-butene and 2-butene and burn it and compare the E1, E2 values. Always E2 will be less, because the molecule is stable with less potential energy. Common product both gives the same carbon dioxide and water. So therefore, when the common product is there, you can compare and see that the justification is the more the hyperconjugable hydrogens. So therefore, it is beautifully explained. Okay, right? Like this, if a compound is little bit complicated, like for example, if you have a 6 carbons and hydrogens will be 12 hydrogens. So it can be a 1 butene, right, 1 hexene, it can be a 2 hexene, it can be a 3 hexene, or some branches also you can have like this. You can have a so many branches like this. You can have a one more carbon. This is a branched hexene. You too can have a so let us designate A, B, C, D, E, F. These are all having the same molecular formula, isn't it? 1 hexene, 2 hexene, 3 hexene. This is 2,3-dimethyl 2-butene. This is 3-methyl 1-pentene. This is 3,3-dimethyl 1-butene. Like this, all these are all having the same this one, but arrange them in the stability order, which is the most stable one. Means before coming to a conclusion that stability, you can go for the calculation of number of hyperconjugable hydrogens. It is not the total hydrogens, inevitably it is all will have the same 12 hydrogens. But in this case, these are the only 2 hydrogens which shows hyperconjugation. Rest will become waste, and the hydrogen on the double bond is called vinylic, that also only allylic hydrogen. So number of hyperconjugable hydrogens are 2. In this case, this side 3 are there, that side 2 are there, so 5 are there. So it is somewhat better one, more stable than this one. That's what 2-butene is more stable than. Here you have a 2 plus 2, that is 4 hyperconjugable hydrogens are there. In this case 3, 3, 3, 3, all the 12 are eligible. I think it is the maximum. No alkene will have a more than this 12. This is the maximum hyperconjugable containing alkene is nothing but this one. This is tetramethyl ethylene, you can also say. In this case it is 0, 1 hyperconjugable. There is 1 hydrogen is there which can shows hyperconjugation. In this case 0. So in some alkenes the hydrogens are 12 is there, but still hyperconjugable hydrogen is 0. See, all lot of variation is there in the. So now the arrange the stability order means the most stable comes D. So D is the number 1 stable, most stable one. Then comes the B comes. Then comes the 4 one, that is C. Then comes the 2 one, that is A. Then comes the E. Then comes the lastly F. That means when you burn all these compounds, maximum energy you will get from the F, minimum energy you get from the D. That is the stability order. So here on what basis you are able to guess? Practically you can verify it through the burning and doing. But with heat of hydrogenation you cannot, because all will not give the same. These 3 you can. You add hydrogen in this case, because the final product will be all in N-hexane, N-hexane, N-hexane. When final product is same, the energy can be comparable. Out of these 3, which will have the heat of hydrogenation more means, and the unstable one, that is 1 hexene will have higher heat of hydrogenation. You are adding hydrogen, getting N-hexane, there also energy is released, but the end product will be the N-hexane. So you can say heat of hydrogenation among these 3, this is high, next comes 4, next comes. More the hyperconjugation, the stability will be more, its potential energy will be less, energy liberated will be less. So it is the more hyperconjugation, therefore energy liberated minimum. This is the most stable. This is the stability, not the energy order. It is stability order, right? Stability order. The more stable, less stable, and so on. F will be the minimum stable. So a set of alkenes, if it is given, you can go for this counting the number of hyperconjugable hydrogens and correlate the asked question versus this number of hydrogens like this.